Welcome back. In this video, we're going to wrap up section 10.1, the language of hypothesis testing. Now, in our last video, we were looking at how to set up the null and alternative hypotheses. So let's pull up again the three examples we were looking at, and we'll see how to set up the null and alternative hypotheses in each case. Okay, remember our first example. We said that in 2008, it's believed that 62% of American adults regularly volunteered their time for charity work. But a researcher believes that this percentage is different today. And now different is a key word here. The researcher doesn't know if the percentage has increased or decreased. She just wants to know if it's changed. Now, the hypothesis deals with a population proportion, P. If there's been no change since 2008, then the proportion is still 0.62. So our null hypothesis is written as HO, P equals 0.62. Now note, by the way, that when our question is about a percentage, we'll usually write it as a proportion between 0 and 1. So we'll write 62% as 0.62. And now, since the researcher believes that the percentage is different today, we'll write the alternative hypothesis as H1, P is not equal to 0.62. And again, remember that we'll call this a two-tailed hypothesis, or we'll say that we're conducting a two-tailed test. Remember, our second example was about the true mean length of cell phone calls. In 2006, the mean length of a call was 3¼ minutes. The researcher believes that the mean length of a call has increased since then. So, the hypothesis deals with a population mean, mu. If there's been no change in the mean length of a cell phone call since 2006, then the mean now is 3¼ minutes. And so we'll write our null hypothesis as HO, mu equals 3.25. Since the researcher believes that the mean length of the call has increased, our alternative hypothesis is written as H1, mu is greater than 3.25. And remember that when the alternative hypothesis has a greater than sign, we'll call this a right-tailed test. And finally, remember the wine bottling problem. In the past, using the old equipment, the standard deviation of the amount of wine dispensed into the bottles was 0.23 ounces. But now, using the new equipment, the researcher believes that the standard deviation has decreased. So, our hypothesis deals with a population standard deviation. And remember, the symbol for that is the Greek letter sigma. Now, if the standard deviation has not changed, then it's still equal to 0.23. So we'll write our null hypothesis as HO, sigma equals 0.23. And since the researcher believes that if there's been any change, the standard deviation should have decreased, so she writes the alternative hypothesis as H1, sigma is less than 0.23. And remember then that this would be called a left-tailed test. Now, we'll wrap up section 10.1 by talking about type 1 and 2 errors. And we'll start talking about the conclusion to a hypothesis test. The example we're going to use to illustrate these ideas is the situation of a criminal trial in the American court system. Now, this is the very common and standard example that we use to illustrate these ideas, because the logic of a criminal trial is pretty much exactly the same as the logic of a hypothesis test. So in a criminal trial, we always begin with the assumption that the defendant is innocent, right? We say innocent until proven guilty. This is like how in a hypothesis test we begin with a null hypothesis and we run the test under the assumption that the null hypothesis is true. So in a criminal trial, the null hypothesis is that the defendant is innocent. Then what happens? Well, the district attorney presents evidence that the defendant is guilty. This corresponds to collecting and examining data in a hypothesis test. And finally, the jury has to deliberate under the assumption that the defendant is innocent unless the evidence makes that unlikely beyond a reasonable doubt. And so what happens? If the evidence is strong, the jury rejects the assumption that the defendant is innocent and returns a verdict of guilty. If the evidence is weak, the jury fails to reject the assumption that the defendant is innocent and returns a verdict of not guilty. Now notice, if the evidence is weak, we don't conclude that the defendant is innocent. We say he's not guilty. The trial isn't set up to prove that he's innocent. We begin with the assumption that he's innocent, and then look at evidence that would cause us to reject that assumption. So now, let's think more about the two outcomes of guilty and not guilty. Suppose that the defendant is found guilty when he really is guilty. Then this decision would be correct. Or suppose that the defendant is found not guilty when he really is innocent. Then again, this decision would be correct. So there are two ways the trial could turn out where the correct conclusion was drawn. But now this points to two other situations where the conclusion would be an error. Suppose that the defendant is found guilty when he really is innocent. Then clearly this decision would be an error. And this type of error is called a type 1 error. A type 1 error is when we reject the null hypothesis when the null hypothesis was really true. In a criminal case, we can think of the assumption that the defendant is innocent as the null hypothesis. If we reject that assumption and find him guilty when he's really innocent, then that's an error. It's a type 1 error, rejecting the null hypothesis in favor of the alternative when the null hypothesis was really true. And finally, suppose the defendant is found not guilty when he really is guilty. Well, this decision is an error, and we call this a type 2 error. A type 2 error is when we fail to reject the null hypothesis in favor of the alternative, but the alternative is really true. Type 1 error is also known as a false positive. Examples of this would be a test that shows a woman is pregnant when in reality she's not, or when a doctor concludes that a patient is sick when in fact he's not. And then type 2 error is also known as a false negative. An example of this is a test which shows a woman is not pregnant when in reality she is. So a nice way to think about this is with a 2x2 grid. The columns represent reality. Either HO is true or H1 is true. And the rows represent the conclusion to the test. Either we fail to reject HO or we reject HO. And if we reject HO when it was really true, then we've committed a type 1 error and we have a false positive. If we fail to reject HO when H1 was really true, then we've committed a type 2 error and we have a false negative. Now let's go back to our examples and think about what it would mean to make a type 1 or 2 error. In our first example, the null hypothesis was that P, the true proportion of adults who volunteer for charity work, is 0.62. And we had a two-sided alternative. That is, the alternative was that P was not equal to 0.62. So a type 1 error would occur if we concluded that the true proportion P were not equal to 0.62 when in fact it really was. However, if the true proportion P had changed and was in fact different than 0.62, then a type 2 error would occur if we failed to reject the null hypothesis and conclude that the true percentage had changed. In our second example, the null hypothesis was that the true mean length of calls made on cell phones was 3.25 minutes. and our alternative hypothesis was that this mean had increased. So a type 1 error would occur if we rejected the null hypothesis and concluded that the mean had increased when in fact it had not. However, if the mean had in fact increased, then we commit a type 2 error if we fail to reject the null hypothesis in favor of the alternative. So, how do we know if we've made an error? Well, in general, we never know. And the reason for this is that, generally speaking, we never know everything about the population that we're studying. But what we can try to do is to control the probability of making an error. And so we can actually think about the probability of each of these kinds of errors. We'll denote the probability of a type 1 error as alpha, and we denote the probability of a type 2 error as the Greek letter beta. Now, of the two of these probabilities, the one we're really going to be concerned with in our course is alpha, the probability of making a type 1 error. And this probability, alpha, is also referred to as the level of significance of the test. Now, there are certain commonly used values for alpha, values such as 0.05 or 0.10. But whatever our alpha level, we're going to see as we go on that it's important that it's set prior to collecting our data. Now, what do we need to consider when setting the value for alpha? Well, since alpha is the probability of rejecting the null hypothesis if the null is really true, then we need to consider the consequences of wrongly rejecting the null hypothesis. In other words, how big a problem is it if we reject the null hypothesis when the null is really true? If there are severe consequences to this, then we can set the alpha level to be small, say 0.05 or even 0.01. However, there's no free lunch. If we set alpha to be very, very small, then that has the effect of raising the bar in a sense and making it more difficult to reject the null hypothesis. Well, that's fine, but then by raising the bar and making it more difficult to reject the null hypothesis, we're increasing the probability that we don't reject the null hypothesis when it's really false. And that's the probability of type 2 error. So, in other words, reducing the probability of type 1 error has the effect of increasing the probability of type 2 error, and vice versa.